Great. So let's start. Hi Abhinav, hi Balaji, hi Binta, hi Gopi. Hello Kamal, Neerav, Noor, and Ross. Great. So let's start. Okay. So I'll just give you a very brief of what we've discussed so far. Okay. All right. So far, what we've discussed is first we divided our data set into training and test set. Just give me a second. I'll just put my phone on silent. Okay. Okay. So thank you, Gopi, for letting me know. So I'm only able to see the questions from 7 a.m. onwards. Could you post the question again? Okay, sure. I will actually separately answer this. Okay, I'll separately answer this. It's a good question. All right, wonderful. So far, what we have done is, with respect to the MNIST data, we have divided data set into training and test samples. Then we trained the classifier using training data set. And we tested using test data. Okay. And then we tried to understand how to measure performance. That's where we were. We created something called confusion matrix. Then we computed the precision and recall out of confusion matrix. The confusion matrix was the one where on the x-axis, as in horizontally, we had the real values, and as columns, as rows, we had the real values, and as columns, we had predicted values, right? So that was our confusion matrix. And this we did for 5 and not 5 classifier, the binary classifier. And then we talked about precision and recall. Precision shows how error-free is our classifier, and recall shows how much it is able to recall, as in how much it is able to recollect without worrying about errors. Okay, so precision and recall are kind of opposite things, and that's what we were discussing. So based on your project, based on the work at hand, the task at hand, you would use precision as your measure or recall as your measure. Okay. In certain problems, you would require high precision, while in other projects you would require low precision but high recall. Okay. Say for example, if we have to detect videos that are unsafe for kids and display those videos, here we cannot we do not have a bandwidth to make a mistake. Okay, so here we do not have a bandwidth to make mistakes, and that's where we need precision. This is where we need precision, and in case of, let's say, we are trying to detect whether somebody who is going out is a shoplifter, and in case somebody is detected as shoplifter, we'll just check their the items they're carrying and the bill they have paid. Okay, so in this case we have a bandwidth to make mistakes. In this case we have a bandwidth to make mistake, but if you miss out on some shoplifter, what would happen is if we miss out on shoplifter, we'll make losses there, and we will not be able to catch somebody. But if somebody is detected as shoplifter, we can always check the bill and let them go. So here it is okay to tag somebody who is not a shoplifter as shoplifter, but here in this particular project or in this particular kind of work, we do not have bandwidth, or we do not have the luxury to make mistakes, right? Therefore, here we need high precision, and here we need low precision. Okay, so the classifier gives us the details about the score, and then we choose a target value, and based on the target value, based on our requirement of precision, we will pick the target value. Okay, so we took this example. I think this is where we were, right? Yes. Any questions on this before we go further? I'm just worried that we all are on the same page. Okay, no questions so far? Okay. Let me just go ahead with F and score then. All right, wonderful. So in case of SGD classifier, classification is done on the basis of score as calculated by decision function in SGD classifier. And what was that? The decision score was how far is a data point, how far is a particular reading or particular data point away from the separating line. Okay, that was the decision function, the score. Okay, and score above a certain threshold is classified as positive class, and score below a certain threshold is classified as negative class. Okay, meaning score above the distance away from the line that is separating the two features, that threshold is, if it is higher, then the chance of it being 5 is higher and not 5 is lower, like that, in that way. Okay, so moving ahead, so threshold can be set to achieve a certain precision and recall as required. Let's take an example here. Okay, so in this example, we will be, say, setting a threshold and computing the precision recall manually. Okay, imagine that we are drawing a line here. This is the threshold. This is the value of classifying as 5. Okay, this is, let's say, this is our threshold. Okay, so if we draw the line here, we calculated that our precision was 75%, while recall was 100% because we were able to recall all the 5s, though we did make mistake. Okay, therefore, recall is 100%, and precision is bad because precision is lower, 75%, because we have two things that are classified as 5, but they're not really 5. Okay, so when we go here, the precision further improves because one of the tools that were classified as 5 is no longer being classified as 5, and therefore the precision is little better, but it's still not 100% because we have one extra 6 this side. So out of total number of identified 5s, 1, 2, 3, 4, out of 4, there's still a mistake. So here you can see that 4 by 5 is what our accuracy is, right? As in precision is. While 4 by 6, the recall rate, we were able to recall how many? 4 out of total number of 1 and 2, 6 5s, right? And therefore the recall rate is going down. We are not able to recall all the numbers. So if we increase the threshold further, right? So we did the computation last time, and I think all of you answered well. And the precision would become 100%. Here the precision would become 100%, but recall rate would go down, right? Because all of the 5s that have been identified, they all are correct, right? There is no wrong thing that has been classified as 5. So its precision has gone 100%, but since we have missed out on 3 of the 5s, therefore our recall rate has gone down. All right. So what we understood is all right. A question from Bintao. What does score refer to along axis? Okay. And precision, recall, and F1. The score is actually the value, the way based on our loss function, the loss function that we use. Based on that function, the score we will be computing, right? And then we'll be we'll be computing the score based on our penalty and loss functions. And then, not penalty, loss function, based on loss function, we'll be computing the score. And then we will put in the various thresholds to check which one is good enough for our case. Okay? So score does not refer to precision, recall, or F1. Score is the actual value, as in how score is basically a particular value which is computing the similarity index, you can say, or which is basically the distance of a particular value from the separating line, the hyperplane. Okay, that's the score, our loss function. Okay. And so what we've understood is increasing precision reduces recall and vice versa. If you increase precision, the recall will drop down, as we just saw. And raising the threshold increases precision and decreases recall. Okay, so the threshold, you can say score is kind of similarity index, or you can say score is kind of how we are matching, how far are our how well is our particular character, particular image matching the model, you can say that. So it's basically based on loss function. Okay, I think understanding score would be better if you think in terms of loss function, that every digit, if you are classifying something as 5, and every digit would be having certain score with respect to 5. So in this case, so every digit, so when we are classifying this as 5, not 5, so we'll be computing that how far is 8 from the hyperplane and so on. That is the score. Okay, it thought it makes sense. And we'll be doing that for all the characters. So this threshold here means that all of these have a lower score. As we keep on growing up, going to the left, the score keeps on improving. Okay. All right. So for threshold 0, classifier correctly classifies 5 as 5 for threshold 2. Okay. Let me. Yeah. So loss function we discussed earlier. There is a mathematical function to compute loss function. Okay. So when we are so there's a mathematical function to compute loss function, and that was based on computing the distance from the hyperplane. Okay. Okay. And all right. Now, to find out the scores, you can always use a function called decision function. Okay. So for say SGD classifier, what you can do is you can say after fitting or after generating the model, what you can do is you can use a function called decision function and pass some digit, and it would give you the scores. It will give you how far, how well some digit is 5. How well some digit is 5. Okay. So let me just show you. I think that'll be better. Okay, so we are using this machine learning / classification.ipynb. Okay, so it is available in our GitHub repository inside cloudxlab/mm. Okay, github.com/cloudxlab/mm. Okay, so this is where we were. So you can say that this is if we are classifying here, okay, looks like this is a little unstable. Okay, it is still. Okay, great. This is very bad. Okay, so we are going to run all above. Okay, so let's say this is our our classifier, and we have already run fit here above. So let me just show you. Yeah, so this is where we train the model, and after we train the model, what we have is here, when we call the descent function over the sum digit, it gives us a scores. Okay, it gives us a score. This is how closely this digit is matching. Is 5. This is that score. Okay. Now, if we say y scores greater than threshold, then it will compare this threshold against the scores, and it will be telling us true or false. Okay, so if our threshold is higher, as in 20,000, then digit will be classified as not 5. Okay, so okay, and therefore the recall rate will be going down. So if our threshold will keep on going up, right, the recall rate will go down. Now, the next thing is let's try to use a particular descent function. So we can actually use the cross-val predict earlier, the way we did the cross-val predict for fitting, as in generating the model. Remember what was cross-val predict? Cross-val predict took an algorithm, created these many folds out of your data, and then trained this algorithm, as in fit this algorithm on this data set with these labels, right? And here we are saying that give us the decision function as the output. Okay, this is what we are saying here. So once we run that, we get these scores. Okay, these scores are basically the numbers telling us the various scores of the digits. All right. Okay, let me go up. Okay, so for X-train data, it has produced the scores. And yeah, so what does SGD classifier stand for? This is the name of the SGD classifier algorithm that we created earlier. So, right, you remember this? This is what we did earlier. So SGD classifier represents SGD classifier and random state. Okay. Question from Gopi, how do we interpret F and F score? Can it be used? I'll just come back to that. So yeah, and going further, a question from Bintao. Why train 5 is, yes, that's right, because we converted our problem into 5 not 5. That's why train 5 is equal to that. Good, very good. All right, so this is where we are. Now, these are the various scores. Let's go down further. So these are the scores of this Y, okay, as in this data, X-train data. It shows that, what is the size of this one? It's going to take some time. Yeah, 60,000, right? So for all the records that we have in the input, it has computed the Y scores of the same, okay? It has computed the Y scores of the same, and Y scores basically signify that how each digit in the X train away from the model, okay? How well each digit in X train, how well it's being classified as 5. That's what Y scores represent. Okay. Now, using a function, here we are importing a function called precision underscore recall underscore curve. So using this function, what we can compute is, we can compute the precisions, recalls, and threshold. Okay. So we are saying that this was our original data, Y train 5. Okay. This is the actual, and this is predicted. Okay, this is actual, this is predicted. So when we call precision recall curve, it is going to give us 3 values. It is going to give us precisions, recalls, and thresholds. Okay. So what is it going to do? Let me repeat what it's actually doing. So it's going to I'm showing here. So you can see that these are the how should I say? These are the actual labels of the values. These are the actual labels of the values, and these are the various scores. Okay, these are the various scores. So what it is going to do is, it's going to put the threshold just the way we did in the diagram, just the way we did in diagram here, right? This is what it is going to do. It is going to increase the threshold from left to right, and then compute precision and recall. Okay, so we have the scores of each of these digits. We have the scores of each of the digits right now. Okay, we have scores in Y underscore scores, and we also have the name of the digits here. Okay, so for this threshold, it was classified as yes or no, and then what it is going to do is, as part of here, it's going to assume a threshold here, and then compute all the things that have been that would be classified as 5. That means on the leftmost one, when the threshold is really low, everything will be classified as 5. That means recall rate will be higher and precision will be lower, and so on. So it's going to vary. This function, what you see here, what it is going to do is, it's going to vary the threshold from very low score to very high score and compute precisions. Okay, and along with that, it will report the threshold. Okay, so it's going to basically do this work for us of giving us this data, showing all the three values. Okay, so for one, each threshold is going to compute precision and it's going to compute recall rate the way we were doing manually just now. And once that is done, we can use these three columns and plot all these three values so that we can visually see what's going on. We can visually see what's going on. So let me show you. And here we are basically defining a function which can plot the recall rate. Now this function, first of all, sets the size of the figure and then plots these. Okay. It says that threshold is on x-axis and precisions are y-axis. Okay. We are removing, I think, the last one. Okay. Colon -1 as in, okay. Then we are putting a label on it. This is, I think, blue, right? Yes. Yeah, this is blue, this is green. Okay, so we're basically plotting threshold versus precision, threshold versus recalls, and we're putting the labels, we are putting the legend, and we are right? We are limiting the y from 0 to 1. Okay, so when we do that, this is the kind of plot that we get. Okay, so it's very clear that as we are increasing the threshold, as we are, this one is, okay, so let me see if we can fit it in this screen. Why did that fit? This is better. Okay. Okay. So what is it that we're trying to do? We are trying to observe how precision and recall varies with the threshold. Okay, that's what we're trying to do. So we are trying to do, what we're trying to do is we're going to start with a very low threshold, meaning let everything get classified as 5. And then we are going to increase threshold. What does it mean by increasing threshold? At every point of time, we are going to compare the scores. And then based on the comparison, we are going to count how many were counted as 5, right? And then we'll compare that value. We'll calculate the confusion matrix at every point. Okay, for every threshold, we are going to compute the confusion matrix. Confusion matrix was knowing that how many were actually actually 5 and how many were classified as 5, and then how many were actually not 5 and classified as not 5, and so on. So we compute those 4 values and then we compute the precision and recall, right? So what we're doing here, for a very low threshold value of the score, we are going to, starting from the very low threshold value of the score, we're going to compare it with this score and then compare the actual versus the predicted based on this threshold, and then see how is our precision and recall varying. Okay. So a question from Gopi: what is y train 5 and y scores inside the brackets mean? This, I think you got the answer, no? Line number 32, thank you. Okay, so here, y train 5, what was y train 5? We converted our y's into 5 not 5, correct? Y train, if you remember, but after splitting our data, these are the labels that shows that it is 0 or 1, or 2 or 3, the actual prediction. Okay, 0, 1, 2, 3, up to 9, right? So there what we see that we converted that problem into binary by comparing each value with the 0, each value with a 5. Okay, and the white train was true or false. True in case if the particular value is 5, and false otherwise if it's not 5. Okay. All right. So did that answer your question? No? Okay. So white train 5, I'll just show you. I think that is better. Okay. So white train 5 is the actual false true kind of thing. How did we compute white train 5? White train 5 was computed as y underscore train equals to 5. That's how it was computed. Okay. So you can take a look at Y train. What was Y train? Y train was the values starting from all those values from the X side that were the labels, right? Okay, we converted this into a binary classification. Okay, now going up. And the Y scores are how for each of the record, each of the images in the test data set, what we did was we compared the score. We compared the score as in how much it is matching with 5. That's the score. Okay, that's how you can look at it. Okay. Higher value of score means that a value is very well matching with 5. Lower value of 5, lower value of score means the particular digit or particular image is not matching with 5. Okay, good, very good set of questions. Now let me answer a few more questions. A question from Noor. I thought we would decide the threshold. Do we not have control over? Of course, threshold is something that we decide. Here, we'll decide threshold based on our project. And right now, we are trying to see how see our recall and precision and output quality as we vary threshold. Okay, if we have lower threshold, what will happen? If we have higher threshold, what will happen? Okay. All right. So a question from Vinta, why do you set the range of precision recall as :-5? Okay, :-5, -1, what does it do? It basically takes all the values from here, right? So let me just check. So if I have precisions, right? So we have, what is the length of precisions? Okay, these many. And I'm just wondering why it is show. Okay. All right, so it is 5 this, and this one is okay. So it has removed one last value probably. And why would it do that? I think it has removed one value, the value where it was strictly 1. I think that's the one it has removed. But it wouldn't make much of a difference even if we do this. Okay. Interesting. Interesting. Let me just check a few more things. So all right. And what happens in this case? This is okay. So this is an array from this to this. That's all right. Okay. So it's probably removing one of the values. That's all. Hmm. Okay. So I think all right. I'll look into this part soon. This is what does it do? Like if I have an empty array, like if I say a equals np dot array, and I have this, all right? So it basically is excluding last value. Okay. All right. So it is basically removing the, so our hypothesis was right. So it is essentially removing the last value. For some reason, I think the extreme one is what is being removed. I think I got it. You know what it is? Okay, I'll explain. So what's happening is when precision, so if you think about the extreme value, right? Extreme value, let me go back where we were in our diagram. So if you go back here, okay, go back here, right? If your threshold is here, what will happen is your recall rate is 100%, right? Your recall rate is 100%. And your, okay, for here, right? Here, if you go here, sorry, this for the right extreme, that's what we're removing. So in the right extreme, what's happening is for the right extreme here is going to divide by 0. Okay, it's going to divide by 0. That's what is happening. So precision is how many were classified as, okay, so let me think. For one of the values, it's going to divide by 0, and that's why it's avoiding. Okay. In this case, what's going to happen in the last case, let's say threshold is here. Okay, okay. Right, right. So essentially the threshold is computed, has to be here somewhere. That's why it is. So one of the values have to be removed from here. That's right. So threshold is only up to somewhere here, because when you are classifying threshold as the highest, this one of the values are going to be 0. So here what will happen is out of the total that were classified as 5 will be 0 divided by how many 5 were there. Okay, and okay, let me just think about it a bit. So here what's happening when we are going to the right, all the values that are classified as 5 divided by the actual values, so it's going down, and precision is 100% when we go to this side. Okay, Okay. Yeah, yeah. So basically, when we are on extreme right, we are going to get 0 out of 0, 0 by 0 in case of precision, right? That's why we are removing the last value. Okay, let me say it again. So how do we compute the precision? Precision is this is, I think, better example. So let's take this case. Okay, so how do we compute precision? Total number of values here divided by correct values. So this is divided by total values, right? So here it is 1 2 3 4 divided by 5, correct? 4 divided by 5, right? This is okay, right? So precision is 1 2 3 4 5, correct? And when you keep on moving it to this here, right? So precision will become 100%, right? Precision will become 100%. And if you move this threshold to the extreme right, what will happen is 0 by 0, correct? So in this case, it will become 0 by 0 plus 0, right? So if you move that's why we have removed the last value. Okay, I'll just put it here. Okay. Okay. Very good question. All right, I think that clears the question. Okay, so let's move on. Any other questions at this point? All right, so in order to avoid the divide by 0, we are removing that threshold, value. Sorry, we are removing the precision calculation for this, the rightmost one. Okay. All right, let's move on. Now, so here what we saw was that as we kept on going from left to right, yeah, the recall rate kept on dropping while the precision kept on increasing. Yes, go ahead, Noor. That's right. That's right. So that's right. So we had already calculated the precision and okay. So precision. How do I go with the length? Okay, I'll just show you this. Okay, length of precision is how much? Okay, so if I say precisions and I say L minus 1, just show you print. Let me just that's a very good question. So let's just find out why it is so. Okay, so yes, we had already computed the ones. Okay, I think this is better. Thank you, Noor, for that question. All right, all right. So I think that part is already taken care while doing the computation of various values of threshold. While doing the threshold, instead of having equal values as precision and recall, I think that is already covered here. So I think this is a better answer. Okay, so all right, I think we got the answer. All right. So we essentially have removed the threshold is calculated one less than the total values, one less than the total values. Okay. So the length of threshold is one less than recalls and precisions. Okay. Why? Because I mean the same reason. It will basically lead to the divide by zero error, and it doesn't make sense to put take the threshold. Okay. So all right, thank you. So the question that we were trying to answer is what is wrong with here. Instead of giving precisions as such, we are removing the last element. Okay, and why is that? Because since the number of threshold values are one less than the length of thresholds is one less than recalls and precisions, therefore we need to remove the last element so that we can plot it properly. Okay, the number of threshold is one less than the two. Great, let's move on. All right. So what we saw just now is, as we are going from a very low threshold, okay, low threshold of marking something as 5, as we are increasing that, our precision is of course going to decrease, while recall rate is increasing, right? This makes sense. Now, the same thing if you plot it on the graph like this. Okay, here we are basically plotting recalls and precisions. So this is how it looks like. Okay, this is how it looks like. My question is, here we can actually remove this and plot it completely. Let me see how it looks like. Right, here we can do that. Right, so you can see that as recall grows, precision drops, and precision improves as recall drops. Okay, now there is a very important graph called ROC. Receiver Operating Characteristic Curve is another common tool that is used with binary classifiers. It is very similar to this curve. Okay, but instead of plotting precision versus recall, we plot something called true positive rate against false positive rate. Okay, so this is again a very important curve. Okay, true positive as in true positive means how well we are classifying the right ones as correct ones, and false positive means meaning how true positive rate means, true positive means 5 got classified as 5. False positive means not 5 was classified as 5. False positive. Okay. So so this is another curve. So as you here basically, ideally all of these must be, all of the classifiers, the most intelligent classifiers should do that everything should be true positive. There should be 0 false positive. Okay. While in case of a random classifier, like something which is just classifying, doing a coin toss without looking at the image. If you're just doing a coin toss and classifying it as 5 not 5, what would happen is total number of things that were classified as 5 and total number of things that got classified as not 5, they will be equal. So the line will come like this. Okay, so we are trying to describe and understand what is ROC. It's the full form is receiver operating characteristic, and receiver operating characteristic is this curve is quite useful in understanding the behavior of a particular algorithm. Okay, this is very useful. Okay, sorry, Kamal. I think I missed your question. Okay, before I proceed, a question from Kamal was, I have a question, something a little earlier. Please explain this step. Okay, y scores equals to SCD classifier dot decision function. Okay, here we are basically computing the score. How well some digit is matching with 5. Okay. Input parameter is one of the digits that we had randomly selected earlier. Okay, one of the image. So you can just check, let me show you what it means by some digit here. Some digit is one of the image that we were using everywhere. Okay, this was one example that we were using mostly. Okay, this descent function basically gives us very quickly how each digit is, how a particular digit is being classified as, classified positively, as in classified as 5. Yes, how much the algorithm, how much the argument that is being passed is being classified. Let me just put the sentence here so it'll make more sense. Okay. Okay, so this is the thing that the question that Kamal has asked. Now, here all we are doing is, after we have trained our classifier, we are checking whether a particular digit, how well the particular digit is matching. And how we are checking? By instead of true and false, we are just checking the score. Okay, we are just checking the scores. Here, y scores is a misnomer. It's a single value. It's not multiple values. Correct. We are just finding the score for 1. All right. No worries. I think others would have the same doubt. And okay, I think we are all okay so far. All right, so this is what you're asking. So we computed, we checked the score of each digit, then we moved ahead and compared this with a particular threshold. And if the threshold is lower, as in lower, it is classified as true. If the threshold we keep increasing, it will not be classified as true, as in it will not be considered as 5. Okay. Now, if we do that, if we keep on, keep varying threshold and keep noting how many total values were classified as 5 and not 5, and we compute the recalls and precisions for various thresholds, then we would get a curve like this. Okay, if we keep varying and do the calculation of 0.5, 5.05 for all the values in the data set and compute the precision and recall rate, this is how it will look like. Okay, this is the place where precision and recall are equal. All right. Moving ahead. Now, another way, the last one that we wanted to, okay, this is done. All right. The last one, the last matrix is ROC curve. Okay. Also okay. So question, there's a question from Vinta. Is the even point 0 here? Where? Which part, Vinta? Okay, go up. This one. Here. Okay, so you're saying, so question is, it is always such that the precision and recall will be matching at 0? Is that your question? Okay, so as per my understanding, it's not always true that for threshold 0, the recall rate and precisions will be equal. Okay, it's not guaranteed. It's not guaranteed. Therefore, you generally have to, okay, you generally have to plot this graph. Okay, and I'm just trying to locate. There was F1 also. All right. So there was something called, yeah, I'll come back to that. There was something called F1 also. There were some questions related to F1 score, and that one I need to explain because we will be using these things again. Okay. So earlier, what we had done was we had, let me just write it down here. Okay. Do we have a graph for F1? Not here. Let me explain it. Okay. Okay. So, yeah. Okay. Let me again, since we have understood the precision and talked about precision recall very much. So there is another thing called F1 score. What is F1 score? F1 score is harmonic mean of precision plus recall. Okay. Precision and recall. Okay. So if you look at it, the equation is like this: 2 by F1 equals 1 by recall plus 1 by precision. This is what is our F1 score. Okay, so F1 score essentially means that both should be good. If F1 score is great, then precision and recall both will be great. Okay, but that essentially means that F1 will be great only for very small values. Okay, so let me ask you this. Here in this formula, which one is true? F1 is lesser of smaller of recall and precision. Is that true? Okay, is it true? In this formula, so F1 is smaller than recall, smaller than the smallest of recall and precision. Is this true? Okay. All right. All right. So yes. So F1, actually F1 by 2, okay, will be smaller than the both the values. So the way you have to look at it is that even if let's say since precision and recall are lesser than 1, okay, both of these values are lesser than 1. So precision multiplied by recall is always going to be multiplication of both. So unless precision and recall both are 1, okay, only in that case what will happen is that numerator will be really high, right? And denominator will be 2. So the value of F1 will be 1 only in the case where precision is perfect as well as recall rate is perfect. Okay. Otherwise, the F1 will be varying like this. I think I should show you this. Okay. Okay, like this. So how do you take the break? So what will happen is in case of Scikit, let me just show you. Yes, it is very much possible to prepare the, should I do that? Okay, so, okay, so what I was trying to describe is that F1 actually will go up something like this, okay, and go till here, and then come back down, okay, something like this. So F1 score is great when both the values, precision and recall, are great. It's going to be smaller than the smallest. Okay, so who is the smaller this side? The blue one is smaller. So the F1 score is going to be less than this. Okay, and as we reach here, then the smaller is this one, so it'll be smaller than this. So F1 score is going to be, the best case scenario for F1 score is this point. Okay, so F1 score indicates that the recall as precision and precision both are good. Both are good. So F1 score is, when we say that we want to maximize F1 score, when we say that our criteria is F1 score, we are saying that we want both precision and recall to be the best. Okay, that's the scenario. Okay, so we talked about few characteristics: precision, recall, and then F1 score. And now let's move on to ROC. Okay, So we can actually do the same thing, the computation of F1 along with the other values. Okay, so we could maybe yeah, we could do that maybe some other time. So okay, so we could actually plot the F1, and you'll know that F we for us, if we really want both precision to be and recall to be great, then we would use F1 score as our criteria. Okay, and it depends on project to project. It is if your project demands that your criteria has to be F1 score, then you will optimize your algorithm in order to maximize F1 score. Okay. All right, now coming back here. So there are a few more questions. Let me go through those questions. Okay, so what is the dotted line here? 0 represents global minimum. Yes, so 0 represents here in this particular case, 0 threshold is the best case scenario. Okay, in case of this algorithm that we use, the 0 is the best case scenario, is the global minimum here. Is global minimum for F1. A question from Gopi was, I asked about whether we can determine overfitting by F1 score or only through ROC curve or something. Okay, so overfitting is determined by generally by, if let's say for a particular data set, the algorithm is giving 100% great results, but for some other sample, it gives bad results. That is generally indication of that it overfit for a particular sample. Okay. All right, so let's move ahead. Great. Okay. A question from Gopi is that in regression, we used root mean square values to measure overfitting, right? In classification, how does it work? In classification, so question is that okay, so on. So in classification, let me rephrase the question. All right. So actually, in the regression, in order to determine overfitting, we observed that our algorithm was giving impeccable results for a certain data set, but not for the other data set. Okay. Now, how do we determine results? In the two, classification and regression is the only difference. Otherwise, the definition of overfitting is same. Okay, definition of overfitting is same. The only thing is measures, the way we are measuring. In case of regression, all we did was we did the root mean square computation, right? RMS value, root mean squares of errors. That's what we computed in case of the regression. But here, the measure is the measure of our overall value is either the F1 score or the precision and recall curves. Okay. The other measure is ROC. So yes, by looking at the F1 scores, we can generally say that it did fit for a certain section of the data, but it did perform really bad for other section of data. So looking at either the F1 score or even precision. So let's just take a case of precision. Let's say we run our algorithm, it worked pretty well and gave a great precision for certain data set, right? But it gave really bad for the other data set. So that generally is is uh, a signal that our algorithm is overfitting. Okay, good. So you can use either of the measures, either precision or F1. Okay. So a question from Gopi is the interpretation is what? Okay. I still do not understand. All right. So how should I say? We basically graphs are for observing that how well is our algorithm doing. Okay, so let me think a bit. So question is by looking at this graph, can we say that it has overfit? Actually, how should I say? If something has overfit, right? Here, let's say this. Okay. So what would happen if something is overfitting? Okay, something is overfitting. Okay. So when something is the algorithm is overfitting, what will it give is for every value, it's going to give very correct results. And okay, so the scores are going to be perfect. Scores are going to be perfect. That's what it is going to do. And I think this one should do. Yeah, you're right. You're right. If I have to determine if an algorithm is overfitting, probably this ROC curve will be a better representative. Okay, better representative. Okay, but the best representative for overfitting is that if you have like 3-4 samples of data, and for each sample the algorithm is doing for one of the samples the algorithm is doing really great but not for other, that for unknown data, that's generally a mark of overfitting. Okay, so for any of these cases what we have discussed just now, whether precision or for let's say take a case of precision, the precision is going to be really great, really great for this if the algorithm has overfit. Okay, really great for the data it has seen so far, and really poor for the data it has not seen so far. Okay, that would be the the meaning of overfitting. But it's a good question, and one should keep in mind. All right, so great. All right, let's start with ROC curve. See if I can try it well. I have to do other computations. Oh, it says, till what point did I run? All right, so far things are okay. All right. The other measures, correct. The test set should have about the same accuracy and not overfitting. Thank you, Ross. That's precisely what it means. Okay. Great, great. So far we've learned about confusion matrix, precision, recall, and reference code. Let's talk about ROC curve. ROC curve is very similar to reference code, but uses a different matrix. It uses true positive rate and false positive rate. True positive rate is same as recall rate, as okay, meaning how many of the total it has been able to recall. Okay, false positive rate is okay. So false positive rate is how many are false positive divided by false positive plus true negative. Okay, so basically the okay, so yeah. So false positive rate and true positive rate is the criteria for ROC. And right, this one plots the graph like this. Okay. Here, what you see is when we draw a graph like this, on y-axis we have true positive rate and false positive rate. False positive rate is when the false positive is 0, the true positive, as in the total number of fives identified as 5, is really high. Okay, false positive as in things that were classified as 5 are increasing. Okay, so as we try to increase, as the true positive rate increases, the false positive rate is also increasing. Okay, this is the, so as for basically the non-fives are being classified as 5 if we try to increase the true positive rate. This is what it is. So on the increase of after a point of time, if we try to decrease the threshold, or we okay, so here okay, so what we are trying to demonstrate here is that when we try to overcome the, when we try to make our algorithm work better by recalling everything, recalling everything as 5, whichever is 5, trying to match it, it's going to match something which is non-5 as well. This is how it is. So ideally this graph should look like this. This graph should look like perfect one, meaning 0 false positive rate, and at 0 false positive rate, the true positive rate is 1. Ideally, it should be perfectly like this. Okay, perfectly like this. But in reality, it is somewhere like this. All right. While if we have a random classifier, which will basically give equal number of true positive and false positives, right? Therefore, it will look like a straight line. Okay, so the best case scenario will be when it classifies everything as correct. That means the false positive rate will be maximum, as well as the true positive rate will be maximum. Okay, so this is the purely random classifier. Moving ahead, so higher the recall rate, higher is false positive. Okay, so the good classifier, the best case scenario is that classifier would go like this. Okay, a person who can identify 5 as 5 perfectly without making mistake would give the result as 100% here and no false positive. All right, So basically, we are trying to maximize the area under the curve. A great algorithm has the bigger area than the bad algorithm. Okay, and the worst algorithm is probably a purely random classifier. Okay, and all right, so this is how it looks like, and so scikit-learn provides a function to compute the ROC score, again in the same package as scalar matrix, ROC underscore AUC score, and AUC means area under the curve. All right. So here ROC underscore AUC score gives you the value like this, and here it is far above 0.5. That means the algorithm is good enough. So if we plot the random forest classifier versus RCD, we find that random forest classifier is doing far better than the RCD classifier. See that? Random forest classifier is doing far better. Okay. So let's try to plot this. T is not defined. Where T is not defined? Here. All right. So here we are trying to fit the random classifier, random forest classifier. Here, random forest classifier is basically we are using random forest classifier with crossval with 3 folds, and we're getting the results. Okay. Our question is, what is K in this line? Okay. So basically here, right? K is the color probably. Okay. K is probably the color. All right. Okay. Thank you, Noor. Thank you. Okay. When we plot like this, it means FPR is on x-axis, TPR is on y-axis. Okay. Noor's question is, what's the difference in plotting like this and like the way earlier we do, right? Here we are saying FPR is going to be on y-axis and TPR is going to be x-axis. If you wanted both of them to be plotted against some other variable, then we'll use them. Okay. So we can plot multiple charts on one diagram. That's what we're doing. We plotted this and this. Okay. Is that your question? It's not confusing. So this is X and this is Y. Okay. So we can actually plot multiple things on a same chart. And when we have to pass x-axis and y-axis for every plot. Okay, that's fine. So that's fine. Okay. Otherwise, if you don't plot multiple multiple graphs on one figure, we won't be able to compare things. All right. So great. Let's go down. Yeah. So this is what we were discussing. Here, what we're discussing is that if you plot the random classifier here, random forest classifier with our SGD classifier, you'll see that random classifier is doing a far better job. It's there. It's almost there. Which one has biggest area out of the three? This is the random line. This is the what do you say? Straight line for the purely random one. This is the SGD classifier, and this one is the random forest classifier. So which one has the maximum area under the curve? Correct, the random forest one. Okay. A question from Kamal is, what is PR curve? Okay. Okay, so which one are we talking about here? PR probably is purely random. Is it? Okay, so does it mean, okay, so a question that I'm trying to answer is that what does PR means? Okay, so it could be precision recall, it could be positive rate, it could be the purely random one. I need to understand where it is. Yeah, it is missing on my notebook. Never mind. So Okay. PR curve most likely talks about the precision recall. Okay. Precision recall is probably that curve. Okay. Thank you, Abhinav. So yeah, because there is no such thing called PR curve otherwise. It's basically the precision recall. Okay, just too many acronyms. Okay, and, all right. Okay, so here we are. Okay. Okay. Anyway, I'm actually losing the track of questions. Okay. So as a rule of thumb, you should prefer the precision recall curve whenever the positive class is rare, or when you care more about false positives than false negatives, and ROC curve otherwise. All right. So basically, these are the various ways of judging the error, right? These are various ways of, compare which one is good, which one is bad, right? The thing that we're trying to understand is that how do we measure the error in case of classification. In case of regression, it was far more easier. Just doing the root mean square value actually solved the problem. But in case of classification, we have various measures, and for various kinds of circumstances, we use this one. Okay, if we are worried about precision, then okay, we are worried the cases that we took earlier. If that is the case that we worried about, then we should use the precision recall curve as our way of understanding the output. Okay, as way of fine tuning our output. Okay, while the for rest of the cases, the ROC curve does the good job. Okay, the ROC curve does a good job. All right. So if there is a trade-off between, if you have to take a trade-off between the precision and recall as per the problem statement, then you should generally go ahead with the precision recall kind of curve. And if you have to compare multiple algorithms and pick the one which is doing better, you better choose the ROC curve. Okay, and that's how it is. So there are two things that we are talking about here. One is threshold. Other is selecting the algorithm. Okay, so the selecting the algorithm, the ROC curve does a good job, and the out of that algorithm, if we have to fine tune that one, we might have to select a proper threshold so that we can decide upon precision and recall. All right. Yes, that's right, Kamal. All right, good. So that's the quick way of looking at it. And okay, so we can always compute the area under the curve as well as plot it. Okay, so what we have learned so far is divide the data set into training and test. On the training set, do the train the binary classifier, and that too in multiple folds. Then choose the appropriate metrics for the task, whether you want to go for recall, precision, F1 or ROC. Select precision recall trade-off that fits your need. Compare various models using ROC curve and ROC and area under the curve. ROC AUC curves. Okay. AUC is area under the curve. Yeah. So here you can see that the area under the value is this. All right. So which one? You can see clearly that random forest classifier has a better area under the curve. Right. The perfect algorithm will have 1 as the area under the curve. AUC stands for area under the curve. Question from Gopi. Based on what Ross said earlier, does it mean that we plot the test ROC and training ROC on the same plot, and we can determine optimum model? So here what we have done is we have essentially done the entire classification on the entire, all of these measures have been done on the test data. And once we have realized that random forest is doing the best and we have fine-tuned our model, then we can run on the test data. All of it has been done on the training data, and using the CV equals 3, that is 3 folds, and that's what you've done, the cross validation. Okay, so we don't need to plot the training and test at the same place. Okay, so we can actually determine the performance on the training data, and then once we are 100% sure, then we can run on the test data. All right, so this is what we have learned so far. Now we will learn the multi-class classification after the break. I know it's going a bit slow, but trust me, this is probably the best thing that's happening, and we are going to learn it this way. Okay, so let's take a break for 10 minutes. All right, so should we start? Great to have all of you back. Okay. All right, great. There are a couple of questions that we need to answer. So yes, Ross, question is the gradient boosting is even better than the random forest. That's correct. That's correct. But since gradient boosting requires fine tuning of too many hyperparameters, therefore we have chosen random forest for this example. Thank you, Gopi. All right. And yes, Noor and Gopi, please go ahead. A question from Gopi. With regression, we use something called pipeline. Can we use same here? Yes. And that's something that you should do. Okay. That's something that one should do. All right. So we are assuming that we're going to use pipelines in our full project, end-to-end project. Here we are going into individual algorithm or individual class of problems. Okay. So Noor is saying that can you take a look at this image? Okay. All right. Yeah, this is what we have done so far. Yes, very good. Thank you, Noor. All right. Yeah, this is right. Okay. So yeah, so deciding the algorithm is our duty, while matrix is a function of our project, the work that we do. Okay, based on the work that at hand. All right, so the matrix has to be there based on the project, while the decision algorithm is based on our understanding of data and our the resources available. Some of the algorithms take too much of time, and we don't have that much time to do the calculation and run it. Therefore, the algorithm decision is based on data, the problem at hand, and a function of resources sometimes. All right, great, great. All right. So should we move ahead? Any other question? Wonderful. Wonderful to have a great set of questions. Yes, Kama. Your question was. Okay. Is that your question was we first decide matrix based on the context, then decide on algo to maximize the matrix? Yes, that's right. Okay. Right. So when you care more about false positives than false negatives, okay, and that means the higher care about, as in we are serious about, as in we don't want to say false positives at all, meaning we are looking for precision, then the recall. Okay. All right. Okay. So I think that's good. We can go ahead. Wonderful, wonderful to have a great set of questions, and probably most of you are from very good backgrounds. So I'm really lucky to have great class. All right, now moving ahead. So far what we learned was how to classify one from another, right? Like binary classification, that's what we did. 5 versus not 5. Now, in other cases, we have multi-class classification, right? Multi-class is when you want to classify them into multiple buckets. And our MNIST original was multi-class classification. Okay, so binary classifier distinguish between two classes, while multi-class classifier distinguish between more than two classes. The example of algorithms that we're going to use in case of multi-class classifier is random forest and say Bayes classifier, etc. Okay, so there are two ways there are two ways to do multi-class classification, right? So can we use the same technique what we did for binary for the multi-class? Yes or no? So that's what the idea about these two strategies is. There are two strategies. One is called one versus all. So one versus all means we convert our multi-class problems into binary problems, okay, by the way of these strategies. The first strategy is one versus all, meaning in the case of digits, in the case of MNIST problem, what we are going to do is we are going to classify the images into 10 classes, right? So from 0 to 1. So the first way is to create 10 classifier. First classifier says it's 1, it's 0 or not 0. Second classifier says it's 1 or not 1. Third one says it's 3 or not 3. And for every data, we run every record. We run these 10 classifiers. Okay, and whichever is giving the maximum score, which one is giving the highest score, we pick that. So we take our image, we compare. So first we train all these 10 algorithms. We train all these 10 classifiers: 0 versus all, 1 versus all, 2 versus all, and so on. Okay, 2 and not 2, the way we design 5 and not 5. Similarly, we design 0, not 0, 1, not 0, and so on, right? So we can easily do that. And once we have trained, we have created, let's say, 5 classes, and we trained all of them using the same data. Then we can classify every digit. We pass the digit through every of these, compute the score. Remember the decision score. So we compute the score against every digit. And once that is done, we pick the one which has given the maximum score, right? That means that we would be able to identify n number of classes using n number of classifiers, right? Okay. So this is how it looks like. So we design these 10 one versus all classifiers. Okay. So first one will be 0 versus all, second one will be 1 versus all, and so on. Okay. By default, when we are using SGD, if it notices that your labels have multiple values instead of true false, it uses this strategy by itself. We don't have to do anything at all. We don't have to do anything at all. And internally, this is what it does. It uses OVA, one versus all strategy in this case. Okay, so if we just, instead of y_train_5, we just give y_train in the same method called fit, we are going to get the results. Okay. So internally, it is training 10 separate classifiers. Internally, it is training 10 separate classifiers. Okay. All right. So internally, it has given us the correct results, right? Our sum digit was 5. If you don't believe me, if you just say SGD CLF and say decision function and give some digit, it gives us 10 scores. It gives us 10 scores, which means that it has internally created 10 classifiers, and these are the scores of each of the classifier. And which one is the maximum? This one is the maximum, which is 0, 1, 2, 3, 4, and 5. Okay. All right. So internally, SGD classifier does this. Okay. Okay. They're very good questions. Our first question is from Vidya. What is the difference between classification and clustering? Classification problem separates things into multiple buckets given the training data, while clustering does not have any training data. We have only the data, and then we just have to figure out a matrix on the basis of, we have to separate the values into multiple buckets based on some matrix. Okay, we don't have defined classes in case of clustering. Okay, a question from Gopi is, in case some digit was some other number, SGD classifier.predict would be a different number. Correct, that's right, Gopi. What is the range? What is the range for SGD classifier decision function? So I'm not sure about the range. It varies from negative to positive, huge numbers to small numbers as well. So I'm not sure about the range because it's kind of the number, the decision function. The value is essentially the distance between a particular data point from the hyperplane. Okay, so that's the score. Okay, so it's not a great idea right now to do the scaling, because what we are trying to do is we are trying to make it we are trying to do the computation on the actual numbers. We want to do the computation on actual numbers, and therefore, yeah. But we can do the scaling if we wanted, right? So we can simply say that we can find out the max value, okay? And argmax is a function that could help you, okay? So, yeah. All right, so yes. So a question from Kamal is, it would have been scale, okay, what is the max, there is a max and min, right? So here, right, the max and min would be on the test data, on whatever test data you pass to it, or our X, capital X, if we pass that, it'll give us the score for all of them. From there, you can standardize if you wish, so, but it's not really required. The decision function is something internally that we use. We don't present this data generally on a graph or at the end output. So we don't use standardization so often on the decision function. All right. We let it be the way it is, because internally these values, the decision function is, you remember, it's a distance from a line. Distance from a line. And therefore, the way the function has been designed is to give you distinct values. And I'm not sure if you'll get better results by if you scale it. Or maybe you will get. Okay. All right, but you could give it a shot. All right. Great. So basically we can see that for a particular digit, it has given the great results, as well as we are able to check if check the score of, check that 0, 1, 2, 3, 4, 5. So this is indeed 5. Okay. Now, if you want to use some other strategy, we can use that as well. Okay. So one versus all, under the hood is training 10, SGD under the hood is training 10 classifiers, and it selects the one which is highest score. Okay. All right. Now the second strategy is one versus one. Okay. One versus one. Okay. Meaning it does generate all possible pairs. Okay. Instead of saying one versus all, meaning one versus not one. Okay. Zero versus not zero. And how should I say? So earlier one created 10, but this one created n into n minus 1. Right? So if we had so one versus one creates all pairs, all possible unique pairs. Okay, all possible unique pairs. If we have, say, 0, 1, 2, let's say only these numbers. Okay, and 0, 1, 2. Okay, so it's going to prepare all possible pairs. Okay, whether it's 0 or 1, this is binary classification. 0 or 2, that's another one. Then 1 and 2, and so, right? Had there been, say, 3, 4, 5, 6, and so on, right? 3, 4, 5, and 6. Okay, in one versus one, what happens is it internally generates the all possible pairs such that is 0 versus 1, meaning a one binary classifier that only differentiate between 0 and 1. Okay, then another classifier that differentiate between 0 and 2, 0 and 3, 0 and 4, and so on. Okay, so this way, for this one, for 1, how many classifiers will be there? 0 versus n, how many? 9, right? So I think it will also do 0 versus 0 here. I think 0 or not 0. I'm not sure. Okay, so there'll be these many. So there'll be 9 for this, and 8 for this, 7 for this, and so on. But I'm just wondering that it is supposed to give n into n minus 1 by 2. Okay. I think I got it. I think I got it. So it's going to be, last one is going to be, for say ninth one, is going to be 0 classifiers, right? 0 plus 1 up to 9, correct? These many classifiers. Got it? So for 1, since it's not going to go again with this first one, it's going to start with these pairs. Okay, these pairs. And for 2, it's not going to go with 2 versus 1. It's going to start with 2 versus 2. Okay, so this is how it's going to be. So okay, so basically, and eventually it is going to be how many? 9 into 10 by 2. 9 into 9 plus 1 by 2. All right. So basically, these many classifiers going to train. Okay, so for M to train 1 versus 1, quickly, how many classifiers will be there? Yes? Okay. A question from Kamal. What is the difference between 0 or not 0? In this case, what it is doing is, it is designing the classifier 1 as 0 versus 1, meaning whether something is 0 or not 0. Okay. Second classifier is going to be 0 versus 2, and so on. Okay. So it's basically differentiating between two classes. Earlier we had the two classes as 5 and not 5. Here is 0 and 1, 0 and 2, 0 and 3, and so on. All right. So it creates all possible pairs. Okay, it's going to create two classes. The hyperplane will be drawn for all of these 0 versus 1, 0 versus 2, and so on. All of these, the hyperplane will be drawn. And if you think about that graph that we earlier did, say this is our feature 1, this is our feature 2. On one side it's going to be ones, in this first classifier case, on one side it's going to be zeros, okay, and this side it's going to be ones. All right, so that's how it is. So no, okay, so this side it's going to be 1, and this side is going to be zeros. Okay. And similarly, this kind of classifier is going to create 45. All right, let's take a look. So they're going to be 45. Good. All right. So in order to ask SGD to do OVO, as in 1 versus 1, we need to explicitly mention that. We need to create the 1 versus 1 classifier by passing the algorithm object in the argument. Okay, so 1 versus 1 classifier is going to, here when we say fit OVO underscore OVO CLF underscore fit, and we pass X train and Y train, what's going to do is, based on Y train, it's going to generate 45 instances of SGD classifier. Okay, it's going to generate 45 instances of the SGD classifier, or estimators that we are going to train is 45. All right, and then once we predict, everything else is going to be the same. All right, here you can see that number of estimators is 45. Okay. So here we are training 1 versus 1, and the number of estimators are going to be 45. Let it finish. Okay. Kamal, did I answer your question? No? Okay. It'll be great if you could rephrase it once. What does differentiation between 0 and 1 mean? I understand different differentiation of 0 and not 0. Okay, so what it is going to do is from the training data, it's going to separate, let's say, first 0 and 1, the one where it is, and it's going to compute the distances between the 0 and 1s, and then accordingly, how should I say? So it's going to draw the line based on the two classes, this distance between the two classes. Okay. 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 All right. All right. I hope nobody else has doubts. It's important that you ask the question because there are a lot of things that look obvious, but there is some confusion at any point. Yeah. Okay. That's right. That's right. Come on. Okay. A question from Noor is, so it depends on how many unique data points we have. Here we have unique values from 0 to 9. That's why the unique values of labels, right? That's all. So yes. Okay. What does max iterations imply? Max iterations here imply the number of iterations it's going to do. SGD classifier is an iterative process. It's an iterative process. It keeps on basically guessing the initial value, randomly selecting a value, finding a distance, then moving through the direction which is improving it. So there, it needs to stop after a certain point. So it's generally better to give max iterations in case of SGD. Okay, so yes, the max iteration 20 looks really less, but it is doing pretty well. Okay, if you think about all the features our data has, there are 784 features our data has. So for every iteration, the computation has to be done of all those features, right? Therefore, the max iteration here, even if it looks 20, it is actually good enough. Okay. There is no straight way to design, figure out the max iterations. Okay, so I think a better way to do it would be when I talk about the SGD classifier in detail in the next class called models, training models. Then I'll come back to the variable called max iterations. Okay. All right, so a question from Noor, isn't it overkill to increase max iteration have more data points? Okay, so yes, I think, so basically the reason why we pick SGD classifier is because it scales well and it doesn't require too many data points. As in, it doesn't need to load too much of data in the memory, and therefore we use SGD classifier. We'll go into more details after a while. Okay, this one requires a full treatment, so I would like to give it a little bit more detailed explanation of this. Okay, so I'll hold my temptation to answer the question. Okay. All right, great. So we are able to do the one versus one classification. Okay, let it go. I again run it. Never mind. So now let's learn how to estimate the accuracy. All right. So in case of SGD classifier, we used OVA, one versus all, earlier, and here after training we are just checking using the cross-val, as in the cross-validation technique with 3 folds. So here it is going to give us some results. Let it run. Okay, so here we are using a term called accuracy. Accuracy is basically the outcome divided by total values. Okay, and here again we will be using the same metrics as the binary classification, recall and precision and ROC curve. Okay, we again here will be using the same metrics, but for now let's I want to show you something that we can improve the scaling, improve the outcome just by accuracy. Sorry, I missed the question. Okay, Gopi, you still have the question, or should I answer? So your question is, how do we choose OVA and OVO, right? Let me come back to that one very quickly. Okay. So one versus all does a very good thorough work. Okay. So if our data points are smaller, you can go with OVO, one versus one, because it is going to have 45 estimators. If your data set is smaller, then OVO is okay. But if your data set is big, it is really difficult to use OVO, because the total time consumed is going to be really high. So OVO, the one versus one, does give us a better performance, a better differentiation between one class and another. But one versus all gives us both good results, very good results, as well as in the reasonable amount of time. Okay, so therefore, general choice of classification is one versus A, unless you need to clearly differentiate between two very close by classes. Okay. We will come back to that when we go ahead. Okay. A question from Gopi: how large would you say the data set to not use OVU? Okay. So since on average, not only the data set, but also the number of labels that I used earlier. So if the number of labels actually increase by a couple of more, it would become impossible to use one versus one. Okay. Say for example, it is right now we have 10. So if we had alphabets, say 26, suddenly the total classifier will become more than 500-600, right? So how much will that be? 276, right? If we had, say, 36, into 35 divided by 2. So it will be 630, right, for in case of alphabets. Therefore, it will become impractical to use OVO. All right, great, great. So here we are. One more thing is that we can scale the images quickly and then we can see that the accuracy improves very quickly. Okay, so here we are getting 87%, which is 0.87 accuracy. And here is basically very, it's less than 90%. Okay, but if we just do scalar.fit transform, and here we're just converting the numbers to float 65. Okay, and so by a very simple conversion, the accuracy is suddenly improving. Okay, suddenly the accuracy is becoming this much. So okay, so what we just learned was that we need to tweak our images as well, and we will learn to tweak it as we go ahead to improve the performance of the classifier. Okay, so let me just run it. All right. So once the model is identified, it can be improved by analyzing the type of errors it makes. For the previous multi-class classification example of classifying images digits into digit labels, it can be done by observing the confusion matrix. So we have already done this similar model. Let's continue that one. Okay, so this was the confusion matrix. Remember the confusion matrix? So these were the actual 5, not 5 actual ones, and after prediction, these many were predicted as not 5 and originally not 5, and these many were predicted not 5 while they were originally 5, and these many were predicted as 5 which were originally 5, and these many were predicted as 5 but not 5. So these two are good, right? These two diagonals are good. They are the correct values. So this is these are the correct numbers, as in these many were identified correctly, these many were also identified correctly, while both of these were not identified correctly. So false positive and false negative, both are wrong predictions. Okay, both are wrong predictions. All right. Now, when we draw the confusion matrix here, in our case, they're going to be 10 rows and 10 columns. 0 are predicted at 0 and so on, right? So this is the confusion matrix in case of multi-class. All right. And we could do the same thing here by saying confusion matrix, and it will produce us a matrix with 100 elements showing these numbers, right? So this is where we are. Okay, so it's right now computing the confusion matrix. So you can see that on the diagonal, we have got the best results. We have got the best results. 1 identified as 1 are these many. 2 identified as 2 are these many. 3 identified as 3 are these many. So the maximum numbers are on the diagonal. Okay, on the diagonal. All right. Although there are some numbers here and some numbers say here which are on the higher range. Okay, but it is generally better to visualize it on the graph. Okay, So you can see that here, here you can see that the brighter ones, we have said gray means higher the number, brighter it is going to be, lower the number, the worse it is going to be. Okay, the darker it is going to be. So here you can see that 1 is identified as 1 very clearly. So 1, 1 is never confused with anything. Okay. Similarly, you can see that 7 is okayish. Okay. Even 6 is okayish, but 5 is, you see, a little grayish. Right? Doesn't look clear to you? Okay. All right. So observation from Kamal is 2 is getting mixed with 7. Any other observation you have? Any other observations? Yeah. Okay. 8 and 9 both are kind of. Okay. So here you can see that 5 is looking darker than the other digits. Okay. 5 is looking darker than the other images. Do you see that? Do you realize that 5 is darker? Means 5 is not identified as 5 so much as 4 is identified as 4. Right? So which one do you think is true? Why 5 looks darker than the other digits? Question, option A, fewer 5s in dataset. Second, classifier does not perform well on 5, or both. All right. Darker is closer to 0, that's right. Okay. Wonderful, wonderful suggestions. Okay. So let me again read your question. Darker means closer to 0. 0 is what? This is the our matrix. We are talking about our what do you say, the one that we confusion matrix is what we're talking about. All right. So we are talking about confusion matrix. This is a confusion matrix. Okay. And here these are basically on these are the rows, the truth, and this is the prediction. Okay. So how many of 1 have been identified as correctly? So the number of ones identified correctly. So it's actually both. Okay. There could be a possibility, unless we know it, as Kamal suggested, that since we had already checked that 5 were equal, in that case, yes, 1, but sorry, in that case 2, but in reality, we have to keep this in mind that it could be both, because there could be more 5s than any other number. There could be more 5s than any other number. So it could be both. A question from Kamal, is there a way to put a number in this plot? Maybe we can just enable the legends, or we can enable the labels. I think that should do it. Okay, there should be a possible way. Okay, I'm not very great with the plot, by the way. And okay, so thank you, Gopi. Will it do if I just say plt dot annotate? Let me see how it looks. No, it doesn't. Okay, I think it requires more options. Okay, good. All right, so yes, we can do that. And all right, never mind. So now it's not giving us that great result. So what we're going to do is we are going to highlight the color. First of all, we are going to normalize it. Okay, Kamal, you remember why you wanted to normalize the scores? Here we are normalizing we are going to normalize the true positives. Okay, basically we are going to normalize the confusion matrix values. Okay, so here first thing we did was we said conf mx dot sum. We computed the sum of all. Okay, every row's sum here. Okay, so let me show you what it means here. Okay, so you can see confusion matrix here. We are saying y train and y predicted. Okay, so this is the actual value, right? Sorry, this is the actual value and this is the predicted one. So all it does is it puts here all these values, okay, and these values, okay. So let me give you a clear picture. So yes. Okay. So y predicted is this, x trained is this. For each of these x, what is the y that is predicted? Okay. What is the y that is predicted for each of the value of x? Okay. For each of the pair. Okay. So we have this as the original values and this is the predicted values. Okay. So what we have is, let me show you what it means. Actually, what does this do? Imagine that our y train predicted looks like this. Okay. 1, 2, 3, 4, like this. Okay. And this was actually 1, 3, 3, 3. Okay. So let's take a look at this. All right. So there is only 1 and 3 in this example. There could be 2 and 2 and 4. And say 6. Okay. So what this graph does is it puts the original values on the rows, which means 1, 2, 3, and 4. That's what it has done on the row side. Okay, that's a confusion matrix. On the column side, what it had done is that for this, for one, how many? So how many times? So here on the columns, it does 1. Okay, so it says that 1 has been predicted as 1. So it is 1. Then it takes the second number, 3, and looks at the looks at 3 as predicted as 3. So basically, how should if I have to design this, what will I do? Okay, so I'll start keeping these numbers. It's the way to just create a quick spreadsheet. All right. Let me just try here. Okay, so it will create this. Okay, confusion matrix is computed like this. So this is the original numbers, and these are the predicted numbers. Okay, so this and this are predicted as correct. So the value is 1. This and this are predicted as correct again. So the value is again 1. This and this are predicted correctly. So the value is 2, increased by 1. This and this. So 3 got predicted as 5. How many times? 1. And 4 got predicted as, say, 3 got predicted, and let me just make it equal. Okay. 3 got predicted as 5 ones. 2 got predicted as 2 ones. 2 got predicted, 4 got predicted as 6. How many times? Once. Okay. So this is the confusion matrix. All right. And these will be 0 by default. These will be 0. Method, does it make sense to you? In case of multi-class, this is what it means by confusion matrix. Okay. I hope this is clear to everybody. All right, once we have confusion matrix, we can actually plot this graph, and thanks to Gopi, and here is the, okay. All right. Okay, now the important part that we were talking about is the next thing, since it is looking all good, okay, and we are not able to visualize error because we are kind of being blinded by the diagonal, right? Because diagonals values are insanely bigger. If you see, this is so bigger than all of these, right? So it's important to kind of to basically normalize the values and delete for every row. If we just normalize the values, okay, and fill the diagonal with zeros, and also compute the confusion matrix like this. Okay, so confusion, we are basically computing the sum of all of the values in each row, sum of the all values in each row, and then dividing each number by the sum. Okay, that's what we are doing. So you can see that. Okay, so also we are removing the diagonal. We have removed the diagonal with 0. Actually, I would love to do it without, before doing it, before like this. If not like this, let me see how it looks without. Why? Okay, so all I did was I filled the diagonal of this one with zeros. Okay. Okay. Great. So I think this one looks good. Let me just zoom it a bit. All right. So what we have done here, one is we computed the row sum. Then divided the confusion matrix with the row sum, as in divided each of the row values with the row sums. And then we filled the diagonal with zeros. We made it completely dark. Okay. And then we have plotted this matrix again. We are saying match show with the CMap as plot.cm.gray. Okay. So now what is your observation? Okay. What are your observation now? Yes. So what we did was we removed the diagonal and then plotted the rest. Okay. So Kamal is saying that 8 and 6, 8 and 6. So brighter means it's being classified as something else. Okay. So these brighter means that 5 is being classified as 3 and 3 is being classified as 5. Okay. While 3 is mixed up with 2 and 5. That's correct. 2 and 5. Thank you, Gigi. And 8 and 5. Okay. 8 and 5. Yes. Okay. Did anybody observe these ones? Okay. 7 and 9. Yes. This one also looks brighter. Means there are many 7s which are being confused as 9s. Okay. 7s are being confused as 9s, and 9s are being confused as 7s. Very interesting. Very interesting. Here we see that 5 is being confused as 3, and 3 is being confused as 5. Similarly, here 5 is being also confused as 8. Interesting. What else do you see? 4 and 9. Yes. Yes. Okay. 3 and 5. Yes. Okay. Any other observation do you have? All right. Great, great. So yes, your observations are very right. 8 and 9 columns are bright, meaning many digits are being classified. Yes, this is far more meaningful than the previous one. Correct? Because here we have normalized the value, made the values relative and removed the diagonal. Okay. So, okay, 8 and 9 are bright. Okay. And 3, 5, 5, 3 are abnormally bright. These ones are abnormally bright. Okay. All right. So which means that there is a lot of confusion between these numbers. Okay. So possible solutions at this point are gather more training data for 8s and 9s. Engineer new features that would help the classifier, like number of loops in the images of the digits. Third is pre-process image to make certain features stand out more and analyze individual errors. Okay. Seven and nine are, yes. It's not alone 8 and 9. 7 and 9 are more getting confused. All right. Maybe there's a mistake here, but yes, if you take a look at this, this is 7, right? 7 and 9 are being confused, getting confused. 8 and 9, yes. Okay, sorry. Actually, here it says 8 and 9th column, which is 7th actually. Okay. 1, 2, 3, 4, 5, 6, 7, 8. Right? 8 and 9. Okay, so it's actually 8th column. 7th is the 8th column. Okay, so here again, let me put it the other perspective. Actually, the whole column is brighter. Eighth column is brighter. That's what it means. Okay, the whole column is brighter. That's why many digits are being misclassified as 8 and 9. Okay, so to solve this particular problem, we might have to gather more training data for 8 and 9 and engineer new features that will help classify like number of loops in the image, then pre-process images to make certain features stand out, and then analyze individual errors. Okay, analyze individual errors. Okay. Also, if we take a look at more of this data, the way we plotted earlier, if we just take a look at 3s and 5s and the predicted ones and so on, we'll notice that this is basically the confusion matrix with the visuals. And here, these are actual 3, which were predicted at 3, they worked well. Actual 5 that were predicted as 3, okay, if you look at the actual data, okay, and actual 3 predicted as 5, okay. So yeah, this looks like a doctor's handwriting. All right. And yes. So specifically with 3 and 5, there seems to be some confusion in our algorithm. Okay. Our algorithm isn't performing great with respect to 3 and 5. So basically what's happening here is there's only one line difference, this block and this one, right? So the way it is that if you try to draw say 3, okay, so out of this, right? So if I okay, and draw it like this, okay. So if you see, if I draw a line here, it becomes 5. If I draw a line here, it becomes 3. Okay, so 3 and 5 are actually very similar from the way we are computing it. Since SGD classifier is basically computing these pixel values, as in finding the delta between the pixel values. So just shifting of the pixels is basically difference in the some amount of pixels is not making too much of difference. Okay, it's only minor differences between 3 and 5. Correct. So classifier is quite sensitive to image shifting and rotation. That's another issue with the classifier, SGD classifier that we are using. Since SGD classifier does it per pixel delta, therefore total score for a particular class is similar for both. Okay, and yeah. So you remember each feature, each pixel was a column and so on. So each pixel is kind of weighted. So some of the values, so if some of the values are very similar, okay, therefore the overall delta is not big enough in case of 3 and 5. All right. So the other problem that we notice in these is that the classifier is quite sensitive to shifting and rotation. So we may have to pre-process the image to ensure that they are well centered and not rotated. Okay, so we will continue from here and tomorrow, and then we will also cover the training models tomorrow morning. Okay, great to have all of you in the session. Okay. Thank you, Abhinav. Thank you, Balaji. Thank you, Bindao. Thank you, Gigi. Thank you, Gopi. Thank you, Kamal. Thank you, Nirav. Thank you, Noor. Thank you, Pratik. Thank you, Rosh. Thank you, Shahrukh. I'm sure that as we go ahead, it's going to improve our overall speed, and our learning rate will also improve. Okay, great. And that's what is the gradient descent you will learn. Okay. All right. Have a good day. Bye-bye.